We have a 6,400 fluid ounce water tank we want to fill with water, but it's far away from the faucet and the tank is too heavy for us to carry back when there is water in it. So we gotta use a container to bring the water to the tank. If we use a 640 ounce bucket, we need to do it 10 times. This is basic division. If we use a 16 ounce glass, we need to do it 400 times. If we use an 8 ounce teacup, we need to do it 800 times. What about a spoon that can hold only 1/6 of an ounce? We'll have to carry the water to the tank 38,400 times. If we use a finger to hold one water drop, which is about 0.0016 ounces, then we need to do it 4 million times. That's forever. As we have just seen, the relationship between the volume of the tank, the volume of the container for carrying the water, and the number of times we carry the water is given by this equation. The volume of the tank is a fixed number, which is 6,400 fluid ounces. As we choose smaller containers, this denominator gets smaller, and we observe that the fraction gets bigger. What if we make the denominator really small? We all have learned that we cannot divide by 0 when we learn arithmetic, but dividing by something close to 0 is possible. Let's look at a simple function 1 over x. If the denominator is positive and keeps getting smaller while the numerator stays as 1, our result from the division gets larger and larger and larger, just as what we have seen from the water tank calculations. Basically, we can keep going forever and there is no limit on how large the result can get. That's right, the limit does not exist. We have just attempted to compute the limit of 1 over x as x approaches 0 from the right numerically. And since the y values do not approach a unique value, the limit does not exist. It's easy to see that the function shoots up to a positive infinity by looking at its graph. If x approaches 0 from the left, then since the denominator is negative, the y values approach negative infinity. With these two results, it's not correct to simply write infinity for the two-sided limit. But for another function 1 over x squared, we can actually write infinity since 1 over x squared is positive for any non-zero real number x. It's important to know that being able to write infinity does not mean the limit exists. This infinity means that the function increases without bound. And this limit is called an infinite limit. Here's the intuitive definition, and a bunch of examples of infinite limits. We're not calculating them here. Many of them have a form of finite number over 0, leading the answers to be infinity or negative infinity, depending on the signs. Certain ones do not have that form of finite number over 0. Here's a good example of that. L1 of x approaches negative infinity when x approaches 0 from the right. That's it for infinite limits. If you like this video, please share it with others. I will see you next time.